So thank you everyone for coming. Hello and welcome to the International Day of Women in Statistics and Data Science 2023. I'm Dr. Shayanti Jana from the Indian Institute of Technology, Hyderabad. On behalf of the IDWSDS Program Committee, I extend a warm welcome to all of you for being part of the celebration. Today we have with us Professor Arup Bose from the Indian Statistical Institute, Kolkata, to inaugurate this young researcher session, which is sponsored by the IISA, which is the Indian International Statistical Association, and CWS, which is Caucus for Women in Statistics and Data Science. He is a recipient of several fellowships and awards, including the prestigious Shanti Swarup Bhatnagar Award, and the most recent being the PC Mahalanobis International Award for Lifetime Achievements by the International Statistical Institute, making all of us immensely proud on the international platform. For those of you who are unaware, some of the most prestigious awards in statistics include the International Prize in Statistics, which was awarded this year to an Indian statistician, Professor C.R. Rao, Carl Pearson's Prize, and the PC Mahalanobis Prize, which was awarded to Professor Arup Bose. Professor Bose has an impeccable and rich publication history in reputed journals. He has written 6 books on random matrices, U statistics, and martingale theory. I would like to request Professor Arup Bose to kindly inaugurate this session and encourage all young statisticians and data scientists to pursue this field.
Thank you, Shanti, for that introduction. It's nice to see so many PhD students in statistics, especially in India. As you probably are aware, there are not enough statisticians. And wherever I go to any university, institute, this question, where are the statisticians? So in that sense, this is a very wide open field for you to contribute statistics in whichever sub areas that you're working on vigorously, because the country needs you. And I'm sure there is a line of interesting talks that you are going to give today. But unfortunately, I have classes, so I cannot be here. But it is very nice to meet you all, and I wish you success in your life. Thank you.
Thank you very much, sir, for taking time out of your extremely busy schedule to come here and encourage all the young students. We cannot thank you enough for doing this, but we are really, really honored that you could be part of the celebration today. So let's all thank Professor Arup Bose, and let's get the session started. So there is a video, a greeting video we have from our sponsors, which I'll play, and then I will hand it over to the moderators.
Hello everyone, I'm Shauli Basu. I'm a professor of biostatistics at the University of Minnesota. I'm currently the president-elect for the International Indian Statistical Association, or IISA. I appreciate Dr. Shanti Jana inviting me to speak to you all at this conference celebrating the International Day for Women in Statistics and Data Science. I want to tell you a little bit about myself. I'm originally from Kolkata, India. I did my undergraduate from Residency College, Kolkata, and then my master's in statistics from the Indian Statistical Institute. I did my PhD from the University of Washington and started my faculty position at the University of Minnesota in the United States. I work in the area of statistical genetics. I develop statistical models to detect the genes that could have potential influence on a disease. We know now that diabetes, cancer, blood pressure, many such outcomes you can think of are highly genetic. If we can identify these genes, We can develop cure or treatments based on patients' genetic information. I play a big role in the treatment development process, which is enormously rewarding. There are many such opportunities if you pursue higher studies in statistics. Like me, you could pursue academia and be a teacher or professor. There are opportunities in finance, healthcare, and in data science industry for statisticians. With an undergraduate degree in statistics, you can expect to find employment in a variety of industries such as government, research and development, and in consulting. If you have any questions, please feel free to reach out to IISF. It is an organization who could assist you with making connections and provide you guidance if you're interested in pursuing higher studies in statistics. As a female statistician and as a leader, I would strongly encourage you to consider higher studies in statistics. Thank you for joining the conference to celebrate women in statistics and data science. Have a great rest of the conference.
Okay, so now I will hand it over to the moderators to get the session started with the presentations.
So, hello ladies and gentlemen, welcome to the today's session, which is about young researchers from India, held on the occasion of International Day for Women in Statistics and Data Science 2023. It is a pleasure to have each and every one of you here today. Today's session shows the research of young girl students in different stages of their PhDs, working on statistics across different domains. India is a big and diverse country with citizens across different parts of the country speaking different language. This is similar to the field of statistics and data science, where statistical application can be encountered in many different domains, including government, manufacturing industry, pharmaceutical industry, etc. And the list is endless.
Yeah, so hi everyone, I'm Kapil. So this session is organized to encourage more young girls to pursue higher studies in statistics and related to data science field. So this session will show you that the diversity is how diverse India is, and all speaker comes from different background, different region, and they speak different languages. But one thing is common, that they all have passion for research. So yeah, that's it. And I want to announce some rules for the session, that participants can write their question in chat box, and after the presentation, we will take one question from the participant due to the time constraint, and if time permits, we'll take other questions as well after the whole session. Also, I will request the presenters to complete their presentation within 12 minutes. So we'll be giving a warning before 3 minutes and before 1 minute as well, so that our session we conclude on time. So yeah, thank you everyone. So Apurva can take from here.
So now I would like to introduce our first presenter of today's session, Ms. Jyoti Jagdish Prajapati. She is a PhD student in Department of Mathematics at Institute of Chemical Technology and a project fellow in Agricultural and Ecological Research Unit, Biological Science Division, Indian Statistical Institute, Kiridi. Her today's talk is about identification of realized net shift of 106 invasive alien plant species with factors impacting predicted range expansion and stability, a case study using Indian alien flora. So I would like to invite Ms. Jyoti to present her work.
Thank you. Okay. So this is the agenda of my talk. So problem statement, materials, methods, results, and future directions. So we are working on invasive alien plants. So why we call these plants as invasive? So these plants generally originated in one location, one country, and through some medium they get entered into one other country, suppose your country. And when they get entered, we call them alien. And when they get settled into the environment, we call them introduced. And once they start proliferating, spreading, and affecting indigenous plants, animals, and even your economy, we call them invasive. That's why we call them invasive alien plants. So why is this study important? So from first news down to earth, it says many invasive plants are affecting soil nutrients, pushing indigenous plants throw away all herbivores, and due to on which tigers are dependent. So, and in another news, it says like many invasive plants are affecting causing agricultural loss, affecting indigenous plants, and also causing human health issues. So India has numerous invasive alien species that pose an unprecedented threat to biodiversity, ecosystem, and economic development at different spatial scale. Therefore, it is crucial for us to understand the scenario of species climatic niche between native and invasive range and its influences. Okay, so usually it is observed that climatic space of native range and Indian invasive range is similar. But it has, in some studies for some species, it has been observed that they have occupied novel climatic space. So our hypothesis is to test whether climatic space of these species are conserved or not. So this is the, okay, we are starting with our materials and methods. So first we did the data collection, then data preparation, COU estimation, statistical analysis, and then results. So first we collected first we did the species selection of 220 invasive alien plant species from ELORA database, and then we collected biotic and abiotic variables and also Indian occurrence records from this database. And then we collected the occurrence records, global occurrence records from Global Biodiversity Information Facility, bioclimatic variables, which are 19 from the World Claim, and then the Copenhagen climate class, which has base level classes, tropical, temperate, arid, cold, and polar, that are subdivided into 2 different levels. And then we did the data preparation in 4 steps. So first, for the occurrences, we did data processing by removing missing and duplicates and points which are falling over ocean, and by removing points outside plausible range, and removing sampling bias, with which we are remained with 108 invasive alien plants, and these are the number of occurrence records. And then we remove the species which do not have biotic or abiotic variables, with which we are remained with 100 invasive alien plants. And then we generated the background points from the intersection region of Copenhagen climate of species and the native range, and same with the Indian range. And then we collected the bioclimatic values corresponding to native, Indian, and the background occurrences points. And then later we did the COU estimation. Following this process, where we first did the principal component analysis on bioclimatic space for these native and Indian occurrences range, and even for global. And then we used the first 2 scores of these components to evaluate the occurrence density using bivariate normal distribution as a kernel density function. And then from that, we got the smoother density on native and invasive range. And we used this smoother density to overlap these smoother density over each other, and evaluated the niche overlap value using the Sconner G matrix, which values rise between 0 to 1, which tells no overlap to very high overlap. Using this, we have evaluated the niche estimates, and we also did the niche similarity test and also niche equivalency test. So here niche estimates are unfilling expansion stability, which are the proportion of the marked regions. And then we did the statistical analysis. Following this procedure, we got for species which are for which niches are significantly conserved and niches are not significantly conserved. And these are the results. So first we got the overlap class. So where distribution of Sconner's index of niche overlap species, showing low overlap, moderate overlap, and no overlap. And we also get the distribution of niche estimates for each species, and we found that number of species with highest expansion are this. And also we got the number of highest stability. Okay, and then we got the, so there are total 76 number of species which are showing novel climatic space in Indian range. Okay, and then we did the multivariate analysis. So we used the 7 regression models, where we use these biotic and abiotic variables as independent and Y as our dependent variable, which are the niche estimates. So we did the leave one out cross validation to evaluate model performance. We also identified important variables affecting niche estimates using VIP package NR based on the values greater than 50%. And we also defined the interaction between important variables and niche estimates using partial dependence plot. So these are the results from these models. So first column has the comparison of test mean squared error for expansion, stability, and unfilling. So where expansion stability has the best model as regression tree and unfilling has the best model as Mars. So variable in second column, we have the variable importance where we have got the in expansion stability as the three variables: introduction pathways, MRT, and number of naturalized range as the most influencing variable to the niche expansion and stability, whereas in unfilling, MRT is the most influencing variable for unfilling. So so here in third column, we have the partial dependence plot where we have found that the introduction pathway MRT number of naturalized range is affecting negatively to the expansion, whereas positively to the stability, and MRT is affecting negatively to the unfilling. And then we did the mediation analysis using structural equation model to identify, to investigate the systematized pathways to explain which so direct, indirect, total effect of abiotic and biotic variables to niche estimates using the mediator as abiotic variables. So this is the hypothesized model specification. So which is generally a set of several equations. So here at down, you can see there are it's an example where Y is our niche estimates, X1, X2, X3, X4 to X11 are our independent variables, sorry, abiotic and biotic variables. So here X1, X2, X3 are as our abiotic variables, which are working as a mediator. And yes. So this is the results of our mediation analysis. So here it is the path diagram of SEM model for evaluating the effect of biotic variables and abiotic variables on niche estimates through mediators as abiotic variables. So here we are...
Ms. Jyoti, you have only 3 minutes left. So
okay, thank you. So here we have only represented the significant paths. And among these three niche estimates, we have not represented stability as it is the opposite of expansion. And this is the, and then we have got the estimated direct, indirect, total effect of the variables on niche estimates, where point plots are the standard estimates, and confidence interval is, error bar is the confidence intervals around estimates, and p-value is represented over the dots, where star is marked for the significant variables. So estimates of specific indirect effect of factors on these estimates by mediator were calculated as the sum of product of direct paths, and magnitude and direction of total effect of variables on niche estimates were calculated as the sum of both direct and total indirect effects. So yes, these are the references. So generally, these are these variables and also the species which have shown significant conserve, like which have shown novel climatic space, are the point of concern for our, and they need to be used as in a for a management purpose. Okay, so yes, these are my collaborators. Ashwit Kumar Banerjee from Sun Yat-sen University, Dr. Amya Bhaumik from ICT, and Dr. Abhishek Mukherjee from ISI Girdi. And I would like to express my special thanks to Supervisor Amya Ranjan Bhaumik, Abhishek sir, and Ajit sir for giving me this opportunity to work on this topic, for keeping their belief in me. I would like to thank ICT and ISF for providing us logistic and financial support. I would also like to express gratitude to my respected family. And I also would like to express my gratitude to Sayanti ma'am for giving me this opportunity to work on this, to giving me opportunity to present in this conference. Thank you so much, ma'am, and thank you. Yes.
Thank you so much, Jyoti, for such a nice presentation. There are no such question yet from audience. So I request audience, if you have any question, you can ask it in a chat box so that we can cover it in final Q&A session. So, yeah.
Yeah, so in today's session, our next speaker is Dr. Habiba Khatun, and she has PhD from National Institute of Technology, Rourkela. She has publications in peer-reviewed journal, and she has book chapters. Her research interests are hypothesis testing on parameters and functions of parameters, point and interval estimations using classical and Bayesian approaches, and statistical inference under equality restrictions using complete and censored samples. So her talk is related to the topic. So today the title of the talk is Testing Equality of Quantiles for Several Logistic Populations. Over to you, Dr. Habiba.
Hello. Hello.
Yeah, you are audible.
Okay, and my slides are visible. Yes.
Yes, please go ahead.
Okay. Good afternoon, everyone. Today, my topic is of testing equality of quantiles of several logistic populations. Okay, as we know that the equality of several groups or data can be done through mean and median for the case of statistics. So, for some distributions, the mean and median have coincides. However, their tails are different. So, for this case, how to compare the group of data or how to compare the distributions. So, in order to handle this type of distributions, we are concentrate on the quantile for some distributions. Such that some cases the mean or median are equal, but there are some outliers which cannot be defined by the means or median. So, in this case, the outlier can be defined through their quartiles, that is the percentiles, higher percentiles or lower percentiles. So for this case, we are concentrate on the testing of equality for quantile. And here we have taken up the logistic distribution. So for the problem, suppose that xi1, xi2, xi are the random samples of size ni available from the ith logistic population with the scale location parameter mu I and scale parameter sigma I. In this case, mu I are also the mean and the median for the logistic population. And for the ith logistic population, the keyword quantile is coming up as theta I, which is equal to mu I plus eta sigma 1, where eta can be computed as log of q by 1 minus q, where q is in between 0 and 1. And particularly our interest is to test the hypothesis. Their null hypothesis is h naught, which is theta 1 equal to theta 2 equal to theta k, which is equal to theta, where theta is also an unknown parameter. And the alternative hypothesis is theta I not equal to theta j for some I not equal to z. And from the q with quantile, you can observe that when we taking at q equal to 0.5, then our problem is reduced to test the equality of means, that is mu I, of several logistic populations as well as the median. And when all the means or medians are equal for the several logistic populations, then our problem is equivalent to test the equality of variances of several logistic distributions. So for the several logistic distributions, the log likelihood function, which is given in equation 3.1, and we denote it as log L. Now we have computed the MLEs of the parameters, that is the mu I and sigma I under the whole parameters. Until in 1971 has proved that for the logistic populations, the MLE of the parameter exists, and it can be obtained by solving the two nonlinear system of equations. Next, we construct the log likelihood function under the null hypothesis h naught, and we computed it as by replacing mu I, which is equal to theta minus eta sigma I in our original likelihood function, and in this case we denote the log likelihood function as log L naught. And as similar to the whole parameter space, we have obtained the MLEs under the null hypothesis. That is, we denote it as the restricted MLEs of theta and sigma I. And in this case, we denote the restricted MLEs at theta hat RML and sigma I hat RML. And we know that the MLEs are invariant under the sum or function, so that in this case we can obtain the restricted MLE of mu I as mu I hat RML, which is equal to theta hat RML minus eta into sigma I hat RML. Now, first we applied the well-known asymptotic likelihood ratio test for this case, as in this case the MLE does not have any closed form, so that we have applied the Wald's theorem to the likelihood ratio function. That is, in this case, our likelihood ratio test statistics is denoted as capital lambda, which is equal to -2 log lambda, where lambda is the supremum of lambda is the ratio of supremum of the likelihood function under the null hypothesis with the supremum of the likelihood function under the whole parameter space. And in this case, the likelihood ratio statistics lambda follows the chi-square distribution with k-1 degrees of freedom. And we reject the null hypothesis when capital lambda is greater than chi-square k-1 alpha. And similarly, we compute the power of the test for this case. Now, as we know that the cutoff point of the asymptotic likelihood ratio test works approximately well for the large sample values, but what will happen when we take the small sample values? So in this case, we have applied a modified version of the likelihood ratio test, which is known as the parametric bootstrap likelihood ratio test statistics. In this case, first we obtain the likelihood ratio test statistics using the original sample, and then we generate the bootstrap sample using the bootstrapping method with the restricted MLE of the parameters. That is, we have to generate the sample from the logistic distribution with the location parameter mu I hat RML and the scale parameter sigma I hat RML, and compute the likelihood ratio statistics lambda star based on the sample a large number of times, say capital B times. And in this case, the first short the lambda values, that is the lambda star values, in increasing order, and find the lower cutoff point at the alpha by 2 bth position and the upper cutoff point at 1 minus alpha by 2 into capital Bth position. Then we reject the null hypothesis when the original lambda does not fall in between the lower and upper cutoff point. And we compute the power of the test, which is here the probability of lambda less than the lower cutoff point or the lambda greater than the upper cutoff point. Again, we have applied another computational test which has been proposed by Paul et al. In 2017. And in order to apply this test, first we have modified our null hypothesis here, which I have taken as null hypothesis as zeta equal to 0 and zeta greater than 0 here, since here zeta is always positive. And for the another version of the modified null hypothesis, which is here xi, which is equal to sum of I equal to 1 to n ni theta I minus theta bar square by sigma I. Both the null hypothesis is equivalent to our original null hypothesis h naught. And for both the null hypothesis, we have applied the computational approach test, for which first we have to obtain the MLEs of the original parameter space. Then we have to generate some artificial samples using the restricted MLE and compute the MLEs of the parameters, that is zeta and xi, which we have specified in the modified null hypothesis. And in this case, the MLEs have to be computed also a large number of times, which I say that a times. And also in this case, we have to find the cutoff point by shorting the MLEs of the parameters in an increasing order. And in this case, the cutoff point zeta hat ml, which is equal to zeta naught hat ml, that is the position of 1 minus alpha into a. Here alpha is our significance level, and we compute the power of the test, which is the probability of the rejection of the null hypothesis. Then first in this table, we have given the size of all the test for the 0.95th quantile, that is Q equal to 0.95 and our sample size is 5.5. So from this graph, we can see that the asymptotic likelihood ratio test has the higher power, that is from our nominal label. Here our nominal label is 0.05, that is alpha. So the nominal level is 0.05, but the ALRT, that is the asymptotic likelihood ratio test, has the more higher size than our nominal level. Okay. And all the other three tests has their size, which is around 20% bound of the nominal level. This is the size graph for the fifth quantile, that is for the median and of the logistic distribution. That is, here we have taken that Q is equal to 0.5, and from this graph we can also observe that the asymptotic likelihood ratio test has size which are much higher than our nominal level 0.05. However, all the other three tests have the size which are at 20% bound from our nominal level. This is a table for the three population. From the graph, we have considered for the two population, and here we have considered the K equal to 3, that is 3 population. And in this case, our null hypothesis is theta 1 equal to theta 2 equal to theta 3, which is some unknown parameter theta. And we have varied the location parameter, that is sigma 2 and sigma 3 for the second and third populations. And we have considered several number of sample sizes and several combinations of sample sizes from equal to unequal. And first, in the first 4 columns, we have given the size value for Q equal to 0.95, and in the last 4, we have given for Q equal to 0.5. So from this table also, we can see that the asymptotic likelihood ratio test has had size which are much higher than our nominal level, that is 0.05. However, for the other 3 tests, the size are in the 20% bound of the nominal level, and for the parametric bootstrap likelihood ratio test, that is the PVLRT, the power is much closer to the nominal level, and it has the most frequency that its size are lower than our nominal level. So we can say that the PVLRT test or the parametric bootstrap test is more conservative in terms of attaining the size or nominal level. So as from the size table, we have observed that the asymptotic likelihood ratio test has higher size from our nominal level. So we have discarded it for the power comparison, and for the power comparison, we only select the 3 tests, that is the PVLRT, CAT1 and CAT2. So in this, from this graph, we can say that the CAT1 has higher power than the other, and the PVLRT has lower power, which signifies our size values, that is the PVLRT is the more conservative to attaining the size. So in this case, it has the lower power among the others too. From this table also we can observe the same, and this is the power for 3 populations, and from this table also we can observe that CAT1 has the higher power, followed by CAT2 and followed by PVLRT. Next, first here we have considered 2 examples. So first example is based on the data sets which was the tensile strain data for the denim trousers. The first data set is the tensile strain for manual designing denim trouser, and the second one is the tensile strain for the laser beam designing denim trouser. So from this test, for the data set which both are follows the logistic distribution, we can observe that from the Anderson-Darling test, and for the p-value for the Anderson-Darling test signifies that the logistic distribution fits well to both the data sets. And for this case, we are in this table we have tabulated the p-values for our 4 test procedure for several quantile points. That is, for the 0.28 quantile, we can observe that PVLRT accept the null hypothesis. However, ALRT reject the null hypothesis, and the CAT1, CAT2 is on the boundary line. Next, we have considered the data sets which are related to the strength of the seismic reinforced concrete building. That is, for Panda et al. Has considered an experiment by constructing the concrete using the copper slag, replacing the sand. That is, M20 is the 20% of sand was replaced by the waste copper slag. M60 is the 60% was replaced by the waste copper slag. M100 is it is totally constructed with the waste copper slag. And sorry, also from the Anderson-Darling test,
sorry to interrupt. Last 30 seconds are.
Yeah. from the table that Anderson-Darling case signifies that the logistic distribution fits well to both the data sets, and also for both these data sets we have done the tests for several quantile points. That is, in the we have also seen that the asymptotic likelihood ratio test is not performed well. The CAT1 is the best one, followed by CAT2 and followed by BBLRT. There are some references. I would like to thanks to my supervisor, Dr. Manas Ranjan Tripathi, and my hearty thanks to Shanti ma'am for giving me this opportunity to speak in this conference. Thank you all.
Thanks a lot, Dr. Aviva, for the wonderful talk. And does anyone have any question? I can't see. Yeah. I can't see in the chat box right now. So maybe we can take some question after the session, like when discuss and give their feedback, then we can take it. So with this, please join me to give thanks to Dr. Aviva for such a nice talk. Yeah. So our next speaker today, Priyanka, who is a PhD student in the Department of Mathematics at Indian Institute of Technology, Hyderabad. She holds an undergraduate degree and master's degree in mathematics. And her research area is related to spatial temporal modeling, where she works on Bayesian inference like INLA, AGQ, and variation-based for skewed data set, where she used R. And today's her talk is, the title is Spatial Temporal Modeling for Non-Gaussian Data. So I welcome you, Priyanka. Over to you. If possible, make the full screen.
So now you are able to see my screen?
Yes, everything is perfect.
Okay. So hello everyone. Today's my talk topic is spatio-temporal modeling using adaptive Gauss-Hermite quadrature, that is AGHQ. So first I will give the motivation behind our study, and then I will discuss some motivation and background, introduction and background, and then finally I will discuss about my problem. So Bayesian inference as involves the computing the posterior distribution, and it is very difficult to compute the exact posterior. So for this, we have some traditional methods like Markov chain, Monte Carlo, MCMC, integrated nested Laplace approximation INLA, and adaptive Gauss-Hermite quadrature AGHQ itself. But the INLA has provided us a computational advantage, which is but it is restricted to a fewer number of hyperparameters, that is less than equal to 20. And these old traditional methods assume a normal distribution to approximate our posterior density. But quite often we have some practical problems like rare disease and rare events. So this motivates us to consider the skew distributions for spatio-temporal modeling, and also to develop the methods for high-dimensional skew datasets using AGHQ. So in our study, first we will see the Monte Carlo simulation, and then finally we will implement our method on the large data set. And we would highlight that to deal with such large data sets pose the computational challenges. And one of our primary goal is to build robust and efficient methods for high dimensional skew data sets. So this is how our Bayesian inference looks like. In this case, the posterior density is given like this. And to find this posterior density, first we need to find out the marginal likelihood, which is also known as the normalizing constant. And to approximate this marginal likelihood, here we will focus on the Gauss-Hermite quadrature. And the corresponding adaptive rule is the adaptive Gauss-Hermite quadrature. Since it shifts and scales the nodes and weights for any fixed quadrature rule as per the mode and curvature of the integral. Also, one benefit of the adaptive quadrature is that it requires a Laplace approximation that one is suggested in case of INLA. So also we can write our posterior density like this, where the numerator term is our unnormalized log posterior density. And this is how our posterior means look like for any function f. Now, what is quadrature? So to approximate any integral of any function over a set A, which is approximately same as that of the finite weighted sum of functions evaluations at these nodes, and where W of x denotes the weights. So in this case, these nodes represents the k quadrature points in D dimension. But like when D equal to 1, then this is the simple case of univariate. But we can extend this univariate case to multiple dimension to have these quadrature points in D dimension. So here we will focus only on the product rule extension, and which in that case, these quadrature points look like this. And for the weights, we can just product all the weights corresponding to each quadrature, each dimension. Also, in case of the quadrature, it helps us to put the high weights on the points where the function takes its largest value. So for the Gauss-Hermite quadrature, we need the Hermite polynomials, and this is how the Hermite polynomials look like. And the quadrature points are the points where the Hermite polynomials are 0, and this is how our weights look like. And also this Gauss-Hermite quadrature have some nice properties like this. And one main property of this Gauss-Hermite quadrature is that it gives us the exact approximation for any integral of a function, but no other quadrature perform well in this case. Now the question is that why we need adaptive Gauss-Hermite quadrature, since we have the Gauss-Hermite quadrature as a fixed quadrature. So the first one is that in the posterior density, we have unnormalized posterior. So for this unnormalized posterior, we have the shape and curvature, which varies stochastically with y. And no fixed quadrature rule perform well for all the priors and models. So we need this adaptive rule. And second one is that it requires a Laplace approximation for single quadrature point. And in that case, it the unnormalized posterior is approximating using an appropriate shifted and scale Gaussian distribution. And then we will further use this to approximate our marginal likelihood. So now, like how adaptive Gauss-Hermite quadrature works. So for in this case, first we will define the mode and then the Hessian, which is the negative of precision matrix, and the Cholesky decomposition for the inverse of Hessian. And this is how our approximated marginal likelihood looks like. And it also has some nice properties, same as that of Gauss-Hermite quadrature. That's why we have adaptive Gauss-Hermite quadrature. Now, when we approximated our marginal likelihood with the help of adaptive Gauss-Hermite quadrature, then we will approximate the posterior density using the in normal distribution or skew normal distributions. And since this is a posterior density, so by the definition, we can write this as this. And this is how our posterior means look like in this case at mode. Now, like how the IDWSDS works in case of high dimensional additive models. So in this case, it will just combine the quadrature points for k equal to 1 and the rule that is IDWSDS for k greater than 1. And let us suppose that now we have a model having parameters theta and w, where thetas are hyperparameters and w's are priors. So in this case, our marginal joint density for theta is directly proportional to the joint density. And this is how our marginal joint posterior for w is given. And for k equal to 1, it will give us the same result as suggested by the Turney and Kadani in 1986. So finally, we have the approximated Laplace approximation, which looks like this. And it is defined that we have done some transformation for this theta, that is our lower Cholesky triangle and mode. And the posterior is just approximated by the Gaussian distribution using some parameters. And finally, we have our approximated posterior, which is the finite weighted sum of approximated Gaussian density and the approximated Laplace approximation. So we can make the inferences for W, that is our prior, and any function of it based on the exact posterior samples from the mixture of Gaussian approximation. And but one thing is that the adaptive Gauss-Hermite quadrature is not yet implemented in case of finding out the marginal posterior density. So now I will discuss about my problem. So in my problem, we have taken multivariate normal distribution. In this, Z is our design matrix, which is known from data. And W is our prior with these parameters, which follows the multivariate normal distribution. And Y's are our response variables. And this is what the transformation we have done, and where itas are linear predictors. And our posterior density looks like in this. And to approximate it with the help of skew normal distribution, we have defined a function f of W, which is the log of posterior density, and it looks like this. Now we have the derivatives corresponding to this function f, which is the log of posterior density over W. And these are the first three derivatives. Now, like in case of AGHK in our study, we are going to approximate whatever the posterior density we have with the help of multivariate skew normal distribution. So we have focused on the multivariate skew normal distribution as suggested by Azzalini and Cadane in Capitano in 1999. So they suggested that if we have a density of any variables given like this, where these are the parameters, then we say that this Y follows a multivariate skew normal distribution with these parameters. And here this omega is our diagonal matrix, in which the diagonal entries are just the square roots of this capital omega, and which we can written like the Hadamard product of capital omega and identity matrix. So now, like, since we want to approximate our posterior with the help of multivariate skew normal distribution, so we need some sample moments with the help of which we can approximate. So this is how our sample moments looks like. And I have written only the final results for this because of time constant. So this is how our first derivative looks like and the second derivative. And then finally, we have our third derivative, which will be a tensor, and each entry of tensor will be look like this. Now, like, what's the benefit? What's the advantage that we are dealing with AGHQ for skew normal in our study? So the benefits for this is that the AGHQ provides the flexibility to deal with much more complex models, and also it accommodates more difficult optimization problems. So here are the references that we have used. Thank you.
Do anyone have any question for Priyanka? Not. I have one question. Yeah. So when you mentioned initially that because the distribution is not normal and it's rare, that's why we are not able to use MCMC, and you're using different approach.
No, that's what not I said. I said that
Sorry. Yeah.
Like we have some traditional method, and in all these methods we have approximated our logo posterior with the help of normal distribution. Yes. You can use any method for this case, but like yes, we can find out some data set, like we can see some disease data sets or something that are skewed. So for this one, we can't use the, like, we can use the normal distribution, but it will not give us the like better results. It will be some biased something. So we just want to see that we will use the skew normal distribution to approximate the posterior, and we will see some better results. Or that's why we are.
So my question is, like, let's assume that if with transformation, if you are able to get the normal distribution from skewed one, and you use the traditional MCMC approach and your approach, did you see the computational time differences and overall efficiency of the method?
this MCMC is like very slow. It takes to, for the computational point of view, it takes like number of days or like this. But this INLA provides us the computational advantage, means it will give us the result within seconds. But in this case, like it is restricted to fewer number of hyperparameters, but AGOSK provides us that we can deal with high dimensional parameters also. So we can use MCMC, but this is not that much, will not give us some benefits.
Okay, I have few doubts, but I can take those offline due to constraint of time. So I will reach out to you later on.
Oh, okay, sure.
Yeah. Thanks to everyone. So Apurva, please.
Yeah, so now I want to introduce the discussant of today's session, Mr. Saradi Karthik and Mr. M. V. Shrikanta. Karthik and Shrikanta are pre-final year BTech students of Mathematics and Computing at Indian Institute of Technology, Hyderabad. They both are currently working on a research project of GM ANOVA models for skewed and volatile data. Karthik is a member of IISA and IMS societies and excelled in JEE Mains and Advanced 2021. And Shrikanta qualified for Indian National Maths Olympiad 2020 and also secured AIR 177 in KVPY. Now I would invite Mr. Karthik and Shrikanta for the discussion.
Let me just share my screen.
Yeah.
Is it visible?
Yeah, it's visible.
Yeah. So hello everyone, myself Karthik and we have Shrikanta. We are students of Dr. Sayanti Jana and now we'll summarize and discuss the previous presentations. So starting with Dr. Habiba's work, for a group of distributions, comparing just their means and medians might not suggest equality of distributions. So other statistics are also compared. Specifically in her work, qth quartiles are compared for a set of logistic distributions. And appropriate null and alternative hypotheses are set up. And asymptotic likelihood ratio test, these tests, asymptotic likelihood ratio test, parametric bootstrap likelihood ratio test, and computational approach test are used for hypothesis testing. Finally, simulations are done to compare powers and sizes of tests, and the results are obtained accordingly. We have the next presentation. Yeah, the title of the presentation is Spatiotemporal Modeling Using AGHQ. This is presented by Priyanka. And first of all, let's just break down the title. The spatiotemporal is something that includes both space and time aspects in the data. And Gaussian Hermite quadrature is a numerical analysis method typically used for approximating integrals by a summation over discrete values. And when the fixed quadrature rule is Gaussian Hermite quadrature, the method is called adaptive Gaussian Hermite quadrature. The goal is to extend INLA, short for integrated nested Laplace approximation, given by Ryu and others, which originally was restricted to less than 20 hyperparameters and assumes normal posterior probability. And the extension is done by considering skewed distributions for spatiotemporal setting. Here, the skew normal posterior distribution is used and is approximated by using adaptive Gaussian Hermite quadrature. And it is followed by validation analysis using Monte Carlo simulations and concluded with implementation on a real big data set, where the primary goal was to build fast and efficient methods versus high dimensional skewed data sets. The results are making inferences with AGHQ package gives the flexibility to fit much more complicated models with a little additional code. And AGHQ accommodates for more difficult optimization problems and some computational challenges. Now we'll move to the next presentation. This is a case study by Jyoti on realized niche shift using Indian alien flora. Data set is collected and prepared from ILORA and GBIF and Köppen-Geiger climate classes. COUE estimation is done through a few steps, including PCA, equivalence, and similarity test for niche. And this is done using EcoSpat package in R. For descriptive analysis, Schoner's D-based analysis is used to learn about niche shifts. Then 7 regression models are used for multivariate analysis on 11 biotic and abiotic variables and niche estimate. The results are obtained accordingly. Using structural equation model, mediation analysis is done and power diagrams are obtained. Finally, plots are drawn for estimated direct, indirect, and total effect of variables on niche estimate. That would be the end, and if anyone has any further questions, please do ask.
So thank you, Karthik and Shrikanta. I don't think there are any questions yet in the chat box. So I want to wrap up the event by a thank you note. So I want to take a moment to express the sincere gratitude to everyone who made this session successful. A big thank you to our audience, speakers, and sponsors, and thank you to the Shayanti ma'am also. And a special shout out to our Zoom Tech supporter of the event, Ms. Rukaiya Sheikh from ICT Mumbai. Her technical expertise made this virtual session run smoothly. Thank you all for being part of this event. Have a good day.